Very enjoyable listening to the various talks that illustrate in such amazingly original ways the aspects of quantum mechanics that seem to set it apart most distinctly from Newtonian mechanics. Interference effects, coherence, entanglement, they're all sort of related. But as I see it, all of these aspects of quantum mechanics essentially founded on an aspect, a property of the theory, which is perhaps the most distinct. And that is that quantum mechanics reflects an aspect of nature that we could only know things about ensembles of systems or from multiple measurements of a single system. It's this randomness that underlies quantum phenomena, quantum transitions in particular, that seems to be so distinctive. And yet we take that for granted. And I don't know of very many instances where one has actually made comprehensive tests of that hypothesis. About 12 years ago, I got interested in that question. Essentially, is how random actually are quantum transitions. And it was sort of made my own quantum transition from atomic, molecular, and optical physics into a sort of a nuclear physicist. And it was a very enjoyable time for me. It's sort of experiments that I did with a longtime colleague, Wayne Strange, at my university, and my son, Chris, who was a high school student at the time, to test various kinds of nuclear decay processes, alpha decay, beta decay, electron capture decay, to see whether there was evidence of non-randomness. You can't ever actually prove that something is random, but you can devise tests to see whether the process does not adhere to what physicists and statisticians would call statistical control. Some years later, actually fairly recently, I got interested in this again, as there has been published in the literature over the last at least 10 years, claims that have never been confirmed or refuted or retracted, that there are correlations in the fluctuations of nuclear decay processes, which, if there were, would essentially be a violation of quantum mechanics. The claims that were made were actually more extreme than that there were correlations in the fluctuations of virtually all ostensibly independent stochastic processes. But of course, we can't test all, and I got interested in the specific area of testing it for nuclear decay, because after all, we were set up to do that. The basis for such claims, as I can just tell you sort of briefly, were at least of two kinds. One was, and here's an example of that, this is a histogram of the decay of plutonium-239 constructed in such a way that I'm not going to bother telling you about it, other than to point out that this histogram manifested certain articulations, which the authors of these claims, and these claims have been published in peer-reviewed journals and reviewed journals, and as I say, even as of last year, I had seen claims related to that same issue, that these articulations represented, in some sense, macroscopic states highlighting these fluctuations. Now, I'm not ashamed to tell you at the outset that that aspect of the claims, I think, is, well, totally incorrect. There's no basis for it at all. It's a manifestation only of the way the data were handled. The second type of claim that was made was that if you were to make histograms of some decay process, and here again the published articles show plutonium-239, and you make histograms of the counts that you have made in sequential intervals of time. So you look at these different histograms, that there is a recurrence in the shapes of the histograms. And you could see something like this as a histogram which shows a kind of rabbit ears, and here's another one shows kind of rabbit ears, and here's another that shows kind of rabbit ears. And the claim was made that these, again, represented correlations in the fluctuations of the nuclear decay as they showed up in the histograms. There is no such thing as the shape of a histogram. It depends on how you bin the data. It depends on how you set up the classes in which you categorize the data. But the claim that there was a kind of periodicity, and the claim was made on the order of a half a day, 24 hours, and monthly, in the decay rates of these nuclear processes intrigued me. Because even if there weren't anything true about the shapes of histograms, it was something we wanted to test, the only way that you could really know whether there were correlations in the decay of radioactive nuclei were to examine these decays, time series of decaying nuclei, and apply rigorously various kinds of statistical tests. The experiment that I devised with my colleague Wayne Strange, which I think represented a very clean way, at least in this one aspect, to test whether there are correlations in the fluctuations of nuclear decay, whether there are periodicities to the decay or trends to the decay beyond what we already can explain on the basis of known physics, was to search for these correlated fluctuations in the beta plus positron decay of sodium-22. Sodium-22 have a source, and it decays by emitting a positron. The scheme is over here to become a stable isotope of neon, and emit a neutrino, which does not play a role in the experiments or the analyses that we've done. The positron will annihilate with an ambient electron to give you back-to-back gamma rays, which, by the way, are an entangled state, although I didn't do any experiments with the entanglement in this case. I was interested basically in doing coincidence counting. So these back-to-back gammas would be detected within a coincidence window of 50 nanoseconds. The number of counts in a counting window, a sampling window, which we could call it a bin, was tallied up by a multi-channel scaler. The bin width was about 0.44 seconds. And I needed a word to represent some short word with a B to be the complement of bin, in which I wanted a certain number, 1 hour's worth of bin, so I call it a bag. So 1 hour's worth of collecting samples at 0.44 second width bins made for a bag. And you have to understand then a little bit about how the data were organized in order that I can explain to you what kind of tests we ran. So imagine the time axis runs this way, and each one of these little squares is a counting window, one bin, and we would get a certain number of counts, maybe 180, 210, 160, etc., all the way along. And 1 hour's worth, the 8,192 bins make one bag. And the bags now can be represented as frequencies, the data in the bag. So you could ask the question, how many times in a particular bag did this value, 181, show up? How many times did 182 show up? How many times did 100, so on, like that. And here are all the bags. There were 167 of them in the experiment that we did. We counted straight for 167 hours. These are the frequencies that, if you plotted them, you would make a histogram. And the classes had the finest subdivision that you can make for a discrete experiment like this, is the value characterizing each class differed from a previous and a subsequent value by 1 count. Now, the elementary statistics of nuclear decay, which is reinforced by quantum calculations, goes something like this, and you might very well have already seen this in elementary courses, that the probability of a single decay within a short time interval, that probability is a constant lambda, the characteristic decay rate of that nucleus, times that time interval. This simple expression sort of encapsulates in it the null hypothesis that the decays from time interval to time interval are independent. They don't depend on what happened before. They don't depend on what shall happen afterwards. And by concatenating intervals like this, you could ask such questions as how many nuclei X, what is the probability of X nuclei out of a total of N nuclei decaying, and I won't go through the argument, but it leads to a binomial distribution for X decays out of N nuclei, such that in the limit where the number of nuclei is very large and the probability of a decay is very low. That product, NP, is the mean number of decays, and it leads to a Poisson distribution. And if that mean number is large compared to 1, then this is almost indistinguishable from a Gaussian distribution. And we were working in that range, a mean number of counts of approximately 200, maybe about 194, such that the Gaussian approximation should be very reasonable. So this is an example of what sort of signals that we would get. Here is looking at the kind of the data you get. There's a lot of scatter about a mean number. If we made a histogram of the counts in bag 1, the beginning of the experiment, it fit very well to a Gaussian, Poisson Gaussian distribution. Look at the distribution at a mean somewhat halfway through the experiment. Look at the distributions towards the end of the experiment. We can see if there's any sort of changes. And in all instances, these, in the crudest sort of statistical test, these distributions were Poisson Gaussian as one would expect. The half-life is about 2.6 years, and 167 hours is not very long compared to a half-life of 2.6 years. But the experiment does see that, and if we were to plot the log of the mean decay rate for each bag as a function of the bag number, which is also equivalent to the hour time sequence, you get a scatter that you could fit a maximum likelihood or least squares best fit line, and we fit that to arrive at a decay rate that was very close to what is published in the literature and shows that our work is on track, and there's nothing at this stage that is inexplicable. Now that's the elementary theory of nuclear decay, but a non-elementary theory of nuclear decay does the following, and here's where the tests become fairly powerful. We start then with this time series of nuclear counts. Each one of these x's is the value of our count in a particular bin, where n is over a million bins. Transform the series from this to a different set with 0 mean and 0 slope, 0 trend. Take account of the natural lifetime, correct for that, and then get a transformed time series that should be flat. You have now counted for the decay as you understand it, according to the natural laws of physics, just the natural lifetime. You could then take the Fourier transform of that series of decays, and you get real and imaginary amplitudes at these different frequencies. And you can also do the serial correlation, which is a function that is actually specifically looking for correlations. The tau is the delay from one count to another, and what you're doing is you're multiplying a transformed count at some time by its value tau seconds later, summing over all values of t as they range over the 1 million or so, 1.4, 1.5 million counts. And then you will plot this function as a function of the delayed tau and look to see whether there are peaks and whether those peaks are statistically significant, indicating correlations. Each of these functions, there's a variety of things now that use the data in independent ways and have different distributions. So that if something follows a Poisson distribution the way it's normally examined in nuclear physics tests, doesn't mean that those data will then obey these other distributions that these functions represent. Now, here are your counts again. That's a Poisson or normal distribution with a variance mu, where mu is the mean count. The Fourier amplitudes, you could show that they also follow a normal distribution, but with half the variance. The squared amplitude, each of these squared individually, follows a gamma distribution, and I'm not going to discuss, unless there's an issue with it, but I didn't want to take up time. We're doing sort of trivial things. It's not trivial, but it would take a lot of time to explain, and these are things that could be looked up or discussed afterwards. But they follow a gamma distribution. The power, which is a particularly important experimental quantity, the sum of the squares of the Fourier amplitudes follows an exponential distribution. The modulus, which is the square root of that, is a Rayleigh distribution. The amplitude ratio is a Cauchy distribution. And then the serial correlation coefficients follow a normal distribution with, again, a different variance. All of these different statistical quantities, if nuclear decay is described by quantum physics, and that null hypothesis that I just enunciated for you, there are no free parameters. All of that depends only on the mean count rate that we set up, adjust experimentally, and then that's fixed. I'm not going to worry. These are what those distributions look like. They're real. We could work with them. And here's the results of that first aspect of our testing. Here is an example of the distribution of the real part of the Fourier transform. This is the data. This is not a computer simulation. We have so many counts that the theory, which is the envelope around each of these experimental things, the theory wraps around so tightly that you can't, at this level of visualization, see fluctuations. So this is the distribution of the Fourier amplitudes, the real ones, the distribution of the power spectrum, the Rayleigh distribution for the modulus, and the distribution for the amplitude ratios, and they all agree precisely with what one would expect if the decays were described by this null hypothesis of independence and no correlations. We could do chi-square tests in addition to just the visualization, and they give you reasonable p-values for everything, indicating there's nothing amiss in those distributions. The power spectrum and the serial correlation, I would point out, are related by what's called the Wiener-Khinchin theorem. It's actually a very tedious process to calculate the serial correlation in the way that I described it to you, the way that it was defined. And a much faster way to do that is by making use of the discrete fast Fourier transform, or I would actually call it a discrete Fourier transform. This is the serial correlation at lag k for the discrete data. And one can calculate by this fast Fourier transform algorithm, square the amplitudes and add them together to get the power spectrum and take the inverse discrete Fourier transform. And that gives you expressions that are identical, if the theorem is correct, and one can prove that this works, that these are equivalent expressions to the serial correlation. The only drawback to using a fast Fourier transform routine like that is your data have to be in total number an integer power of 2, and we had a very large integer power of 2. So this is what the decay gave rise to. You're looking over here at the serial correlation coefficients for the nuclear counts. Lags up to the equivalent of about 47 hours, plotted against the standard deviation, because you can show that the distribution is a normal one. And although there's a lot of fluctuation, these peaks do not extend more or less beyond plus or minus 2 sigma. Every once in a while, something a little bit larger than that. But if you do the statistical analysis, you find, again, this is entirely within statistical control. And there's nothing in these fluctuations that signify a statistically significant correlation in the time series. The various correlation coefficients themselves follow a Gaussian distribution. These are the data. This is the theory. And again, a chi-square sort of test shows that the data are matched acceptably by the theory. Here are 3 different ways of looking at the Fourier spectrum of the time series of nuclear counts. Plotting the modulus versus the harmonic number. This is actually the harmonic number divided by 100, and I realize that that's not too visible. Or plotting the log of the power versus the log of the harmonic number. Or plotting the real part of the Fourier transform versus the imaginary part of the transform, and getting a circularly symmetric distribution. These are characteristic, this in particular, and this in particular I'm going to comment on as to their statistical significance. Because if you look at these, I mean, the fact is there's so many harmonics put together in this graph that it looks like a solid line. But the fact is you've got these discrete harmonics, and there are peaks that go up above the common level. And the question is there anything in this distribution that signifies a statistically significant periodicity in the count data? One way to examine that is to test for the statistical significance of the largest peak, because if that is not significant, then neither would be the smaller peaks. And there is a way to argue how to do that. And the argument actually is, if you were following the original slide, which I don't imagine people do, and there's so much information sometimes on a slide that there's no point in trying to read it while the speaker is talking. But the argument given over here to arrive at the probability that the largest element in this power spectrum has occurred by chance is the same argument that leads to the final probability I showed you for in the elementary theory of nuclear decay. That you're given all these spectral peaks, and there are j equals 1/2 n, where n is the total number of bins that you've counted. And you rank them in ascending order, find the maximum, and can work through this probability that n element exceeds some value, the probability that j elements do not exceed that value, and then the probability that at least one element exceeds that value. In any event, you arrive at an expression that you could test the largest Fourier amplitude, the largest power spectral amplitude. And we did that. So here, for example, is a plot of the power spectrum for the nuclear data as a function of harmonic number. Harmonic number 8 had the highest power spectrum. Work out what the mean and the value was, and what one finds is that the largest value of that power spectral amplitude compared to the variance for this exponential distribution is in the ratio 10.72. Inserting into the formula that I had derived before and showed you what it looked like, which is known as the Fisher-Walker test, shows that the probability that a spectral amplitude exceeds this one is about 50%. It's interesting to point out, is if you were working with, as we normally often work with, a Gaussian distribution, and you are more than 3 standard deviations away, the probability of something being larger than that value is a fraction of a percent. And here we are 11 standard deviations from the mean, and the probability is only 50%. And the reason is this is an entirely different distribution. It's the exponential distribution, and it's because it has interesting properties like this that we could use it to test the Fourier amplitude. And we did not find any statistically significant correlations or periodicities in the nuclear counts. Now, we could look specifically and ask the question, if there were some periodic variation in our nuclear data, would we see it? Now, the mean is supposed to be a constant, but in simulating this to put limits on what we could see, so adopted a form that looks like this, where that is, let's say, the mean count, so it's 194 per bin, with an amplitude, beta, sort of the ratio of the periodic component to the mean, at some period t that falls within the length of time, the duration of the total experiment. If that actually characterized the data, that would have consequences in the probabilities, and therefore the time sequence, and in the relative frequencies that would show up in a histogram. Now, how big, or put it this way, how small can beta be such that we would see that? Now, here is the power spectrum where the mean is unmodulated. And you can see there's nothing interesting happening over there. And for that same condition, here is the correlation coefficients plotted as a function of lag time. And again, there's nothing that looks particularly striking over there. And statistical analysis will show you there's nothing happening because all these correlations fall within plus or minus 2 sigma approximately. But if we were to take beta and go from 0 to 0.003, at 0.3% of the mean, you begin to see some activity in the relative intensity of the power spectrum. You can see that something is happening. You can't quite see it yet here in the correlation coefficient. So these are both useful, both needed to kind of see whether there's any kind of inexplicable correlations occurring. And if you go then from 0.003 to 0.005, well, now this kind of knocks your eyes out. Here is a striking effect observed in the power spectrum. And you can see a striking periodicity in the correlation coefficients modulated at 0.5%. Now, the authors of the articles that claim to see periodicities in the histograms claim to see periodicities at levels that were so large that they would have shown up strikingly in the data. What's interesting here is this value of about 0.3%, which is like the threshold for an amplitude of modulation, is so small that you would never see that in the histograms. But you could see that in the statistical tests if that actually reflected the real data. These results that I showed you a short while ago, just the previous slide, were for an assumption of a periodicity that was shorter than the duration of the experiment. If you do an experiment for 100 hours, then you cannot measure a periodicity that is longer than that. But that doesn't mean you can't say anything about the periodicities that could occur longer than the duration of your experiment for the following reason. If you have some periodic effect in the time series of counts, but you stop counting before you get a full period, then what you have actually is the data, let's say the phase of the periodicity is such that the mean count begins to get larger. That's like a trend. It's equivalent almost to a trend. And you could see what happens with trends here. This is the power spectrum of our data before we transform the data to take away the trend due to the natural lifetime. And there is ringing here due to that trend in the low frequency end of the Fourier transform of the correlation coefficients. Fourier transform of the correlation coefficients. With the trend removed, you don't see that ringing anymore. If we were to assume in our simulation a periodicity in the nuclear counts of a period longer than the duration of the experiment, we assume one here for the example that I'm showing you on the slide of maybe a quarter cycle. So we're not seeing a full cycle, but a quarter cycle at 2% modulated mean. You would see, again, that kind of behavior in the low frequency end of the Fourier transform of the correlation coefficients would be a kind of ringing, and we don't see that in the data. Another kind of test, how am I doing here, Herman?
I still have 11 minutes.
I have what?
11.
Okay. Another type of test that we applied, looking for evidence of non-randomness, makes use of what are called runs, a series of alternatives or series of progressions. And in fact, I think the experiments that my colleague, my son, and I had done around the late 1990s were the first to introduce run analysis into nuclear physics. So I wouldn't swear to that, but I don't think I've ever seen it before. A run known as an up-down run is if you have a series of numbers, then the difference between two numbers, if the second minus the first is greater than 0, you could assign a positive one. If it's less than 0, you assign a negative number. And then this binary sequence of positives and negatives constitutes a series of runs, and they have a particular pattern. It's very common to think that randomness means no pattern, but the fact is a completely random set of numbers, if that set of numbers does not exhibit certain kinds of patterns in the distribution of these binary symbols, then you do not have a random sequence. You have to have them. A test that exercise I often give to students, because randomness is a tricky concept, and it's not always easy to recognize it, or sometimes you think you see patterns when there aren't. But I have had students, for example, half the class flip a coin 100 times, or 250 times, 256 actually, a power of 2. And the other half of the class to go home and write down on a sheet of paper what the outcome, heads, tails, would be in that sequence if they imagined, but didn't actually do the flipping, what the sequence of heads and tails would be like. And then to hand it in, and I told them that I could tell them with 97% accuracy who actually did the experiment and who actually wrote the numbers down. And the reason I could do that is because people who are not familiar with what randomness actually implies would write a lot of short things like plus, plus, minus, minus, plus, plus, minus, minus, whereas the actual experiment for 256 torsos would show that you would have to have at least one run of 6 or greater. So you could, I think the IRS, Internal Revenue Service, also uses tricks like that to see who lies on their tax returns. Here are the theoretical prediction for runs, and these red dots are the actual up-down runs in the nuclear data that we have. The red dots fall within the plus or minus 2 sigma, so we see nothing in the runs analysis. Another thing that we looked at is the concept of intervals. If we're looking at a sequence of counts, here, let's say I'm focusing on the count of 100, and then 100 shows up again a little bit later, and you ask, what is the length of that interval between this first appearance and the next one? This also has its own particular distribution, which is a geometric distribution of intervals. And we tested the data against these run analysis of the intervals and find that we get exactly what is expected by statistical control. The last kind of recurrence, last kind of test that I'll talk about just briefly is the idea of a recurrence of histogram shape. As I pointed out, there is no such thing as a histogram shape. But if there were such a thing and you had a series of histograms, the only meaningful way to look at this is that if you had a perfect recurrence, then let's say you've got a value of 10 for the center of the histogram and maybe a 9 to the left and an 8 to the right. And if this actually recurred, you should get something like this, similar to it, at some period later, and again at some period later. And the question is, do we see anything at all like that in the data now expressed in terms of sequences of histograms, each histogram being made up of 1 bag's worth of data. The way that we did this test, let me back up a minute, is to test for non-random frequency intervals in the histograms. Now here now is a histogram of the bags, a schematic picture of what we would have. 194 is the mean. That's at the peak of the histogram. Your histogram is sort of a Gaussian-shaped symmetric function, and here is the class value about which it falls off symmetrically. We asked the question, how many times do we get a value of 194 counts? We look at the first bag, maybe we have it. Look at this bag, maybe it happens. Maybe it happens again. And then the question is, when we see these intervals of what we're looking for, and we look at the class to the left and the class to the right of it, or up and down of it, there'll be certain values. Do those values repeat? And do these values repeat? Because if they don't repeat, then it's meaningless to talk about the recurrence of the histograms. So we look at the intervals. How often do you get that? And we rank the intervals of this central class in descending order. How many, the largest number of times occurs, then the next, then the next, then the next. And we make the corresponding sorting for these numbers that flank it, and that, on this side, and this side, that side, etc. Because after we do that, we now have the intervals of the central value in a highly improbabilistic ordering, one that would not normally occur like that. And the question then is, are these values If they correlate with that one, then they also would be in some highly improbable ordering. But if they don't correlate, then a runs test on these intervals would just show normal randomness again. And so we did the test. 194 is missing because we're looking at the runs analysis on the intervals for numbers below it and numbers above it, for lengths of sequences, the number of times that particular count category appeared. The number of runs observed, the number of runs calculated, and the normalized residual, which is one minus the other divided by the mean. And these are Gaussianly distributed, and so here are the residuals with corresponding probability interpretation, and everything is exactly as what you'd expect if the intervals were ordered by pure chance. So the summary, I say, is the following. The discrete states, which I haven't described to you in detail, but I could later if you should like, were introduced by the analysis and have no bearing whatever on physics. The visual inspection of shapes provide no reliable test of correlations, but the statistical tests that we applied in the case of beta decay of sodium-22 show complete consistency with white noise, no correlation and fluctuations of the nuclear counts, no correlations and fluctuations of the histogram frequencies, and no periodicity in the nuclear counts or count frequencies for time intervals less than 167 hours, or for unexplained trends within a time period of about 35 days, which embraces the claims that were made in the article that had been published, articles that have been published. And we believe that we would have seen such modulation or correlations had that modulation factor, that relative amplitude of the modulation component to the mean decay, being less than about 0.4%. We see no justification for the claim of correlated fluctuations in nuclear decay. In the talk that follows, you'll hear a very different search for which this was not looking for, and some rather striking and interesting conclusions that are not necessarily in any way refuted by these, because we were looking for something different, and the sensitivities that we have here might be very different from those that Dr. Fischbach is going to report. And taking a cue from Sam, I go to the shameless commerce division of MP Silverman. If you want to read more about the nuclear tests that we've done, or about tests on sort of proposals and experiments made for other experiments involving entanglement and coherence and interference, you might like to read one or the other of these books. I would comment on this one book, because this conference is a rather interesting, has a rather interesting correlation with this. In 1995, I wrote a book called More Than One Mystery, which was a use of a phrase from Richard Feynman, who claimed that single particle wave function interference was the only mystery to quantum physics, and that rubbed me the wrong way, because as we're hearing in the conference over here, there are all kinds of other things that are very different from single particle interference that, in a certain sense, is just as mysterious. I don't believe in mysteries, but I think it's different from classical physics, but to use Feynman's terminology, they are at least not the same kind of physics, not the same mechanism. And in that 1995 book, which I proposed some experiments on having like a quantum optics of particles, Henry-Brown twist type experiment with electrons and various kinds of entanglement experiments, most of which could not be done and had not been done, although there have been a lot of interference experiments. Well, in the intervening times, now as this book came out in 2008, and as we hear at the conference, there's all kinds of experiments. And Hasselbach, whom I'm really sorry could not be here, would have reported in part on the Henry-Brown twist experiment with electrons, is both human ingenuity and technological advances have made possible all kinds of things that in the first book were just Gedanken experiments and now are realized in real life. And this is a considerably updated book with more analyses, more experiments, and more results that reflect, in part, the diversity of projects reported here in this conference. And so, thank you for your attention. Alex.
Can you discuss the role, if any, of detector decay or dead time?
I'm trying to remember what we had for the dead time. No, I can't give you numbers on that. We had looked into that, certainly. There's not, it did not play a role in changing the statistics of this.
So if you
it was like a 10 nanosecond rise time to the detectors for the gamma rays. The detection was the detector was a thallium-activated sodium iodide crystal. Responds on the order of about a few nanoseconds. The dead time due to the electronics is what I don't recall. That is taken into account in the time sequences. As I say, there are 8192 bins to an hour's worth of data. That includes what electronic processing time there is, because if you were to multiply 0.44 seconds by, if you were to multiply 8192 times 0.44 seconds, you wouldn't get 1 hour's worth, and the extra time is into the processing time. But I don't have those numbers strictly for you.
Does that obscure your ability to find trends at all? Or to find
No, I don't think so, because the trend that is there that we did see it corresponded precisely to what we'd expect on the basis of the natural lifetime. If there were trends shorter than our sampling window, we wouldn't have seen that. And if there were trends extremely long, way beyond the 35 days or 40 days that we were able to see something, I don't know, we might not see that either, but within that range that we were our intentional range of being sensitive to, I don't think we would have missed trends, wouldn't have missed any trends that were relevant to the papers we were trying to examine.
Can you go back to the slide where you compared it to a simulation?
Wait.
Yes.
Yes.
To the end.
Is this what you mean? No.
No, I think
This-
I thought you did a computer simulation. Next to the last
But
slide.
these are computer simulations. These are the data.
Yeah. No, I don't remember what the slide is. But I had a question that was stimulated by that slide.
Can I come back to you then while you
Sure.
think about it, and I'll take Stephen's question?
Sure.
Okay, go ahead, Steve.
Yeah, this is probably trivial, but when you talk about looking for trends to detect longer periods, would you have been able to see a period of, say, 70 days in which your 35-day trend would be up and then down again?
Let me make sure I understand your question. So within the 167 hours that we took data, would we have been able to see a trend of lasting?
Yeah. No, I'm asking the wrong question.
Oh.
I guess what I'm asking is whether you would be able to see a period of, say, 4 times your...
4 times the duration.
The duration, so that if you had... Would you be able to see if you had a half a period where your trend was
yes, I
halfway
think
up
so.
and then
If
down?
the amplitude, I'm making a guess because I don't recall if we actually did that simulation, but if the modulation amplitude was about 0.3% or larger, I believe the answer to your question would be yes. Yeah. Yes.
This is a general question for clarification. So from the statistics of nuclear decay, are you trying to conclude that the statistics predicted by quantum mechanics are irreducibly random in the sense that you cannot construct a deterministic model that can reproduce these statistical distributions?
Well, I guess I'm giving you a personal opinion to somewhat, I'm sure there would perhaps be disagreement, but the way I look at it, quantum mechanics is a calculational scheme that reflects what nature is telling us, is that the laws of nature are irreducibly statistical. That we could learn about an ensemble of electrons, and that's what we're doing when we work with a wave function, or we can make multiple measurements on a single system, which is what one does in a single trapped ion or electron, but that we, at the micro level like this, is we cannot know, we cannot predict with certainty what the outcome of a single measurement on a single system would be, such as we routinely do with Newtonian mechanics. So I think...
Let's not have a follow-up question with
Yes.
time. So, okay, let's thank our speaker again.